Okay, so today's notes, we're going to start talking about polynomial functions. Our main goal today is to be able to analyze the graphs of polynomial functions. So we're going to start off by taking a look at this graph right here to the left, and we're going to describe some of its characteristics. So the first thing we want to describe is the number of turns that it has. So a turn is considered when my graph changes directions. So I notice that my graph goes from up to down right here, so that would be one turn, goes down from down to going to up, that's a second, third, and here's the fourth turn. Later on in the unit, we might describe these as relative or local minimums and maximums. So if you kind of look at your graph and say, okay, how many mins are there, how many maxes are there, and add them all up, that's what we're talking about for number of turns. So this one has 4. The number of real zeros, we've seen that when we were talking about the quadratics units. When we think about zeros, we think about those x-intercepts. So if I'm looking at this graph and I'm asking myself, how many x-intercepts does it have? It looks like it crosses here, here, and here. So this has 3 real zeros. And then the end behavior is asking me to describe what's happening on the 2 ends of the graph. So I'm going to look first at the right end of the graph. And now this is hard to tell, but there should be arrows on both ends. Okay, so if I look at the right side, so my right end of my graph, it's going up. So to say this, I'm going to say the right end rises. And then I look at the left end of the graph, and that left end is headed off in the negative direction. So I'm going to say the left end falls. So that's just a really quick way to describe some simple things about our function. If you guys do the Guess Who activity, you'll have gone through and kind of figured out that it's super helpful to know how to characterize some characteristics on the graph in order to describe the polynomial. This next portion, we want to be able to say, okay, so if I know the graph looks like this, I can describe a lot of different things about it. But if I'm just given an equation, I don't necessarily know what my graph looks like to start. So we want to start getting into the details of, okay, what if I give you this equation? So in this case, I'm going to give you an even degree polynomial. So even degree means the highest degree in the polynomial is even. So let's do like 3x to the 4th plus 5x squared minus 7x. The highest degree of all of these terms is going to be 4, right? So the degree of this polynomial is it's a 4th degree polynomial. And so what I'm going to do is I want the a value to be positive. So notice that on the degree of 4 term, I have a positive 3 there. So we're going to graph that actually using Desmos to see what that looks like. So y equals 3x to the 4th. Whoops, I did to the 3rd, plus, what did I do? 5x squared plus 7x minus 7x. And the goal is for us to say, okay, what do I notice about this polynomial? So this is an even degree. Okay, I notice that it looks like it touches the x-axis 2 times, so it's got 2 solutions for that one. And both the ends go up. All right, let's try another even degree polynomial. Let's see if we can do any common characteristics or something that's going to happen every single time. So let's try y equals, let's do x to the 6th, because that's even, plus x to the 5th minus 3x squared, plus 4. Okay. All right, so this one, the blue one looks different than the red one. Okay, but I noticed that I've got some similarities. So it's different because this one now has 3 turns. It only has 1 x-intercept. It looks like it only touches that graph one time and bounces right back off of it. Okay, but it's the same because if I look at the red one, both the red and the blue have both ends popping up. Okay, all right, let's try another one. So again, I want another even degree polynomial. And I want this even degree polynomial to have a positive lead coefficient. So I'm going to do positive. Let's do 2x to the 8th. You know, I'm trying to get the highest positive coefficients that I can think of. Minus 4x to the 4th plus 7x cubed. I'm just making these up all over the place. Whoa, these are crazy, huh? Plus 5x minus 3. All right, so now the green one goes back to having 2 intercepts, okay? But the same thing as the blue and the red. The both ends end up pointing up. Okay, so what can I say about an even degree polynomial that has a positive lead coefficient? Okay, I know that if it's even degree and it has a positive coefficient, in all the polynomials that I graph, both ends are going to rise. Okay, what do you think is going to happen if it has a negative lead coefficient? So what if I take all of these graphs and I make that lead coefficient, that a value, negative? So I'm changing all of those from positive to negative. Now look at these graphs. All of these graphs now open down. So if the coefficient is negative, then both ends are going to fall. Okay, now let's try an odd degree. So let's see if that changes anything about that end behavior there. So let's try, I'm going to start with g of x equals, I'm going to erase out all the even ones. Let's start with g of x equals, I want a positive a value, so let's do positive 2. I need an odd degree, so let's do x to the 5th plus 3x squared minus 4. Okay, again, I'm just making these up. It doesn't really matter. Regardless of the polynomial that I have, I should end up seeing the same patterns or the same characteristics for all, right? Because I'm trying to make a generalization. So let's take a look. Y equals 2x to the 5th plus 3x squared. So 2x to the 5th plus 3x squared. And you can try this at home too. You can try it on your own and just kind of come up with different crazy polynomials. Okay, so this one, odd degree, because the highest exponent here, the highest degree I have is 5. And an even or a positive lead coefficient. That positive 2 is attached to that x, is the coefficient on x to the 5th. Okay, so odd degree, even or positive coefficient, positive lead coefficient. We've noticed that we've got so I've got 2 turns here. I only have one x-intercept. I've got one end pointing up and one end pointing down. Okay, let's see if I do another odd degree. So let's do x cubed. That's odd. Positive lead coefficient, right? So I'm making it positive 1 as the lead coefficient here. Minus, let's do 3x squared plus 4x. Oh, let's just do plus 4. Okay, so same thing. I'm noticing I've got another u. It's got 2 turns again. That's kind of cool. And it looks like the right side goes up and the left side goes down. Okay, let's try another one and see if that holds true. So let's try x to the 7th minus 8. Oh, wait, I need more than that. Let's do x. Oh, whoa, that's crazy. Okay. Minus 8x plus minus 2. Wow. Okay, this one looks like it goes down, or so it comes from the bottom, goes up, comes back down, loops down, and then comes back up. Okay, so again, it looks like the left side goes down and the right side goes up. Okay, so what can I say about a positive lead coefficient with an odd degree? It looks like the right end rises while the left end falls. What do we think is going to happen if I change all of those to negatives? Ooh, that one flipped, right? So it went from going from the left to the right. Now it's going from, down from left to right. So the left end now is rising, the right end is falling. Let's see if that holds true when I switch all of these signs. Same thing with the blue graph. And let's check that green graph. Yep, same thing with the green. Now we swapped. Okay, cool. So when the lead coefficient is negative and it's odd degree, the right end will fall and the left end will rise. Okay, so I'm noticing that the even degree, they do the same thing on both ends. The odd degree, they do opposite things on both ends. Okay, and then I like to kind of pick up this pattern. I always like to make it easier on myself, a way to remember these things, right? So the fact that it's positive tells me the right end goes up. The fact that it's negative tells me the right end goes down. And that actually will hold true. The lead coefficient will tell you what the right end of the graph is doing. Okay, so the lead coefficient, or the a value, what we'll often see it written as, lead coefficient, aka the a value, tells us what the right end does. Okay, whether it falls or rises. All right, then we can talk about some other things. We can talk about, well, how can we know exactly how many turns there are? And because this video is kind of running out of time, we're going to just talk a little bit about what happens in these graphs. So if I look at g of x equals x to the fourth versus g of x equals x to the fourth minus 3x squared, I'm noticing this graph has one turn, it looks like. This one has 1, 2, 3. Okay. I will not have any more turns than my degree. And in fact, the number of turns that I'm going to see in my graph is actually always going to be at most 1 less than the degree. So the number of turns is at most 1 less than the degree. And we're using some fancy words to describe those turns. We're now going to start calling them extrema. Extrema for saying like, hey, it's the extreme high or extreme low, right? So I'm seeing a minimum or maximum there. So this one, it looks like I've only got 1. This one I've got 3. Because these are 4th degree polynomials, the highest number of turns I would ever have for either of these two graphs would be 3, right? So 1 less than the degree of the polynomial. Let's see how that plays out with ones down here. Okay, so these ones are all 5th degree polynomials, right? So degree of 5, degree of 5, degree of 5. Okay, this one it looks like I've got kind of no turns, right? So it's actually not actually doing any sort of extrema. This one I've got a max here and a min here, so I've got 2 extrema. And then this one I got 1, 2, 3, I've got 4. And then let's see if that actually worked out, right? So my degree was 5, and all of these numbers are less than 5. The highest one I have is 4, which is 1 less than the degree. All right, so 6th degree. The most I'm thinking I'm going to have is 5 for any of them. If I look at this one, I've got 1. This one I've got 2 mins and 1 max, so 3. This one, 1, 2, 3, 4. That one's hard to tell, but it's 5. Right, so this one was degree of 6. So, and the most I had was 5 turns. At most I can have 5 turns. Whoops. Okay, so what we're noticing is the number of turns is at most 1 less than the degree of the polynomial. There's some other things we can notice too, but I'm going to leave those out for right now. So then last but not least, what we want to be able to do is we want the largest number of possible extrema being turns, given the degree of the function. So again, if I have a 9th degree polynomial, the most number of extrema I can have would be 8, right? So I can have 8 turns at most. 12th degree, 11. 21st degree, 20. And 18th degree, 17. 7th, 6, 26th, 25. That's it. That's all we got for today. I hope that you enjoyed exploring polynomials today.